Today I want to talk to you about some of the top MSP430 design mistakes that we've seen over the years. We've been doing MSP430 designs for over 6 years. We're even a member of TI's MSP430 design network. So these are some of the mistakes that we've seen sometimes get repeated over and over due to a lot of reasons. And there's no reason why your design should be affected really. Once you deal with them, your design is going to be much, much better. So one of the top mistakes that we've sometimes seen are missing decoupling capacitors that are really needed for the design. So every MSP430 is different, but all of them need decoupling capacitors. In this case, the MSP430 F5438 has several pins that need it: AVCC, DVCC1 to DVCC4, and VCore. These are some of the pins. It's not the complete list, but some of them that you really need to watch out for because they need very specific connections. They need specifically decoupling capacitors. In the case of AVCC, you really want to decouple that very, very well because it's the analog voltage and that's used for the ADC. So for good ADC results, you really want to decouple them. So be very, very careful. Make sure that you have all the capacitors. You can take a look at some of TI's MSP430 development boards to see how where the capacitors are needed. Obviously, the data sheet is also going to have that information in it, and you should really follow it as closely as possible to make sure that you're powering the MSP430. One of the other issues we've seen throughout the years are connections to GPIOs that don't have interrupt capabilities. So to be able to take advantage of the MSP430's low power, and that's really one of the biggest advantages of the MSP430, you really need to use interrupts as much as you can. And really not all the GPIOs in the MSP430 have interrupt capabilities. So for the MSP430 F5438, really ports 1 and 2 are the ports that have interrupt capabilities. So you really want to connect all your switches, external connection, all the interrupts from other devices through these pins so that you're alerted and so that you can basically go to low power and leverage the low power features of the MSP430. Another issue is that you have to be very, very careful about how you design the clocks of the MSP430 in your system. The MSP430 is basically designed with two clocks in mind. The first one is the low frequency clock, which is typically a 32 kilohertz input crystal that is used for the real-time clock and various other things, and simply because 32,768 hertz divides very nicely to generate 1 hertz. The other input is very high frequency clock, which is typically in the megahertz range, and you really need that for high speed interfaces, things like that. For example, UART really benefits from an external crystal just to make sure that it's very, very stable. The MSP430 internally has a digitally controlled oscillator that's good for up to 1% basically deviation. So depending on your application, that might be enough or that might be a problem. Interfaces like SPI, for example, is not very specific on the rate, on the frequency, because the master, which is typically the MSP430, is the one that's supplying the clock. Even if the MSP430 were a slave, that wouldn't change. But other interfaces are really, really picky on the speed. If you need very accurate timing, things like that, you really need to put an external crystal out there that's good, and you have to consider the typical things you would consider with a crystal, which is aging, tolerances, and things like that. It's very important to note that the high frequency is going to cause your system to consume more current. So typically what you want to do is run at slower clocks, at slower clock frequencies. That way you basically reduce your current consumption. So if you started designing with the MSP430, one of the most appealing things about it are its ultra low power features, right? Well, to be able to take advantage of that low power, you really, really need to use interrupts. If you can see here in the chart that we provided, the MSP430 consumes typically a couple hundred microamps per megahertz. And really, you can't always scale the speed at which you run, because sometimes you have to meet some deadlines. However, you really need to take advantage of the low power modes. So in LPM 0, for example, you're turning off the CPU and most of the clocks are still operational. So you've reduced your current significantly. LPM 2, LPM 3, and LPM 4 start to turn off various other peripherals and clocks so that you reduce your current further. And of course, you get a huge advantage from the power supply voltage dropping, as you can see there, from 3 volts to 2.2. So the key is use interrupts as much as possible, because that is really going to help you. You do not want to block or do any kind of polling if you can help it, because that's going to cause a lot of wasted CPU cycles waiting for something to occur. So that basically means you have to operate asynchronously. Events have to come in and then you handle them. And you want to keep your interrupt service routines very short. While you're in an interrupt service routine, the first thing that happens when you enter one, the interrupts in the system, the ones that are maskable, get disabled. Another thing that you really need to fully consider is the supply voltage and the effect it has on the system. So we spoke before about the fact that depending on the frequency of the system, your power consumption is going to vary. And of course, the faster you're going, the more current consumption you're going to have. And so there is a dependency between the supply voltage and the frequency. And there really is a minimum. When you go very, very fast, there is a minimum voltage you have to meet. And as you can see here in this case, you really need 2.4. Of course, if you're designing, you really want to be above that just to give yourself enough margin to be able to do this. The other important thing to realize is batteries, their voltage output begins to change with time. And then you need to be very, very careful that you're still meeting the specification while the system is running. And so if the battery voltage dip below the threshold, you're going to have to adjust the system voltage to be able to meet that. Or you design the system to run at a low enough frequency so where the voltage doesn't have any effect really. The other very, very important key to really leveraging the MSP430 is to use the DMA. So the DMA enables you to move data without CPU intervention, and that's key. Because when you wake up the CPU, as you saw in the previous slides, your current consumption is very, very high. When you use the DMA, there's no need to wake up the CPU. Now, because of the way the MSP430 is designed, because of its architecture, the DMA actually requires CPU cycles and might get relieved. But still, the DMA allows you to do higher throughput data transfers without CPU intervention. And that's very, very useful when you're moving ADC data to the RAM and collecting samples for processing later, when you're sending data on the UART, and so you're moving those bytes through the DMA. So the DMA can really have a huge impact on your system, making sure that it stays asleep and making sure you're transferring things quite fast. Thanks for watching this video. You can find more information at www.argenox.com. We have many tutorials and other technical documents you can find useful.